The golden ratio, the divine proportion. Mathematicians have studied the golden ratio's properties since antiquity. It naturally appears in vegetation, on leaves, in flowers. Artists incorporate it into their work, believing it to be the most aesthetically pleasing ratio ever. Architects took it into consideration when constructing ancient buildings like the Parthenon. It is perfect. And that's why I've come here, all the way to Rome, to witness the mathematical beauty of the Parthenon myself. Wait, but what? This doesn't look right. Pantheon. The Parthenon is in Greece. Well, we're here, so let's do some math. Let's start with the columns outside. Each one is 39 feet tall, made from single granite stones that were brought to Rome from Egypt. They're slightly tapered, meaning the top is a little bit smaller than the bottom. Okay, I swear I didn't bring a tape measure to Rome. I'm not that nerdy. These measurements actually come from the Bern Digital Pantheon project in 2005. They used digital scans to measure the radius at the top and bottom of each column. These columns were constructed by hand in 125 AD, so it's actually super amazing how consistent they are. There is one that's a little thicker on the corner. Vitruvius, a famous Roman architect and engineer, preached that structural columns on corners should be 1/50th greater than the others. We love specifics. Speaking of, Vitruvius also stated that columns should have a top-to-bottom ratio of 7 to 8 in order to be most aesthetically pleasing and structurally sound. A ratio is basically a comparison of two numbers. In the case of Vitruvius, he was comparing a measurement from the top of a column to a measurement from the bottom of a column. You can write ratios with colons, or as fractions like this. Looking at the measurements from the Bern project, we can see that the Pantheon columns pass the Vitruvius vibe check. Even that extra large column on the corner has a top to bottom ratio of about 7 to 8. Very cool. Now the ratio that I thought this video was going to be about was the golden ratio, 1.618 to 1. The Parthenon, which we all know is in Athens, Greece, and not Rome, Italy, obviously, has a width to height ratio of 1.618 to 1. We can see if the Pantheon follows that ratio as well using a proportion. A proportion is when we put two ratios together in an equation. So basically, a ratio equals a ratio. So I grabbed some measurements from the MIT website. The width of the Pantheon is 111 feet, and we know that the columns are 39 feet tall. So I'm going to set up a proportion here. On the left, I've got the golden ratio, 1.618 to 1. So the bigger number needs to go on the top of the second ratio, so that would be our 111 feet. And let's figure out how tall the Pantheon would have to be for this golden ratio to work. To solve for one part of a proportion, we can do this thing called cross multiplication. Basically, you take lower left and upper right and you multiply them together, so that would be 111. And then you take the top left and the lower right and multiply them together. And then you can just solve. This is just a one-step equation. We're going to divide by 1.618. And I get 68.6 feet, which means the Pantheon does not fit the golden ratio. It would have to be much taller to do so. Sad Vitruvius is sad. But you know what? It doesn't matter, because the Pantheon has something even cooler than a golden ratio. Yeah, I said it, even cooler. A perfect sphere. Walking into the Pantheon, seeing the concrete dome overhead, you'll find yourself wondering, how the heck is this thing not falling down? The dome has a diameter of 142 feet, almost half a football field, and was constructed with concrete, volcanic matter, and pumice stone. The higher you get, the thinner and lighter the material, hence why it hasn't crashed down by now. The cool thing about this dome is that it's not just a spherical roof put on a rectangular building. It's a perfect sphere. The distance from the floor to the top of the dome is also 142 feet, which means a sphere could be inscribed inside the main room. Inscribed just means that you can fit one shape inside another so perfectly that you would really struggle to separate them.
My greased up head went into the pumpkin no problem, but
it won't budge.
I can't get it out.
Those squares you see on the dome are called coffers. They're sunken panels that I think are there for decoration, and Rick Steves also told me that they make the dome a little lighter all the way at the top. There are 5 rows of 28. I don't know if you've ever cut a pizza into even pieces before, but dividing a circle into 28 even pieces is very weird. Like 8, 16, 32, sure, but 28? Why did the Romans do that? One website says it's because 28 days equals 4 weeks, and that's how long it takes for the moon to return to its position. Makes sense, as the focal point of the dome is a skylight, they call it an oculus, that lets in a circular sunbeam to mark the time of day. Some say the Pantheon is a cosmic union between the sun and moon. And no, there's no glass on that skylight. When it rains inside. Good thing there's holes on the floor. Back to the 28 coffers. The number 28 is also what Greek mathematicians considered to be one of only 4 perfect numbers. The sum of its factors equals the number itself. The factors of 28 are 1, 2, 4, 7, and 14. And yep, that adds up to 28. Bored in study hall? Try to think of the other 3. It might take you a while, the last one's in the 8,000s. So going back to proportions, let's say I want to make a scale model of the Pantheon and I'm going to use a tennis ball as the dome. Alright, a typical tennis ball has a diameter of 2.5 inches. The Pantheon has a diameter of 43 meters. Different units, but that's okay. So basically we want this tennis ball to represent the dome, and we have to figure out if the dome was only 2.5 inches in diameter, how big would this portico have to be so that it's to scale. I'm going to start with a ratio that describes the tennis ball compared to the Pantheon. So the tennis ball's measurement is 2.5 inches, and that corresponds to 43 meters over on the Pantheon. Now, according to the MIT website, the height of this portico is 14 meters. I'm mixing a lot of meters and feet in this video. Sorry, not sorry.
And how many yards to a mile?
Nobody knows.
Now we can solve to figure out how many inches tall the portico should be. And I'm going to use cross multiplication to solve. So I'm going to multiply these 2 together and these 2 together. Starting with the easy ones here, we've got 43x equals 2.5 times 14. That's 35. Now I'm just solving by dividing by 43, and I got 0.81 inches. So if I really were going to build a model of the Pantheon, not saying I'm going to, but if I were, the height of the portico would have to be 0.81 inches. So maybe I would get toothpicks and cut them down to size. No, we're not doing that. I promise I'm not spending my vacation in Rome using proportions to make scale models of the architecture. But I am using proportions almost every day when I buy fruits and vegetables. There's some fruit in there, probably. Okay, so at the moment, €1 is the same as $1.15. All right, 1 cup of gelato was €3. And let's say I want to figure out how many US dollars I was spending on that gelato. So I'm going to set up a proportion. I'm going to put, let's do euros on top, US dollars on the bottom. So €1 is the same as $1.15. Now for the other ratio of this proportion, a cup of gelato is €3, and I want to figure out how many dollars that is. So the x goes on the bottom. And now we cross multiply. 1 times x is easy, that's just x. 3 times 1.15, that's 345. Those are pretty little cups. It was worth it. So while I've never been to Greece, I'm going to go ahead and say that I'm Team Pantheon. Vitruvius-approved columns, perfect spheres, perfect numbers, a ceiling that tells time. What's not to love? So the longer side of the rectangle goes on top. The bigger number, and the 39 here, and we're just going to see